Howdy. Science. New research suggests that Earth formed much earlier than previously thought. It's not too long ago when I talked about the timeline issue. I think it was in the comments section or something. I call it the timeline issue since many things either happened quicker than previously thought earlier, or more, or bigger, or they are more common. You know. The timeline issue, especially when it relates to time. November 22nd, 2022. Now we start. Earth and the other planets in the solar system have been around for longer than previously thought, according to new research into shredded asteroids in distant star system. Yeah. Why? Why they have to go that far in distant star systems? A study published today in the journal Nature Astronomy examines some of the oldest stars in the universe and suggests that stars and planets grow together. It had been thought that planets didn't form until a star had reached its full size. Its full size, probably, I don't know. The Sun formed 4.6 billion years ago from a cloud of gas with the planets forming around it. This is how they think. We have a pretty good idea of how planets form, but one outstanding question we have had is when they form, said Dr. Amy Bonser from Cambridge University's Institute of Astronomy and the study's first author. Does planet formation start early, when the parent star is still growing, or millions of years later? So she is like oxymoroning here already. We have a pretty good idea, but we just don't know. So we have just this kind of construct, what we believe to be true. It might be based on gravitational theory and such things. First they know and then they don't know. The researchers used the Atacama Large Millimeter Array of radio telescopes in Chile to study the atmosphere of white dwarfs, the remains of sun-like stars after their life cycle has come to an end, in search of planetesimals, the building blocks of planets. Some white dwarfs are amazing laboratories because their thin atmosphere are almost like celestial graveyards. The white dwarfs studied are special causes because their atmosphere are polluted with heavy elements such as magnesium, iron, and calcium. This word made me to make this video. There was calcium mentioned, white rivers and such. Anyway, I'm just gathering pieces for, in a way, understanding is still making like a picture out of this white river thing, phenomena. I don't want to call it a mystery. It's not a mystery. We just don't understand it yet. If it is a mystery, for me, mysteries are some things which are kept alive, you know. You want to keep the mystery. That's the mystery, what it is for. But it's not. It's just, there are just so many things still to have been figured out about this thing. But anyway, white dwarfs, magnesium, iron, calcium, which, say the authors, must have been left there by asteroids left over from planet formation that later crashed into the white dwarfs and melted into their atmospheres. Must have. The process of iron sinking to the core while lighter elements float on the surface is what caused the Earth to have an iron-rich core, according to the paper. Yes, if you just think about gravitational things, then it makes perfectly sense. The heavier things go down, the lighter things go up. But they don't talk about their interactions with electromagnetic currents and such things. Attraction. You know, plus and minus. Attracting or repelling. Planet formation is generally believed to begin in a disk of hydrogen, helium, and particles of ices and dust. Orbiting a young star, as the dust particles combine, planetesimals emerge and get larger over time to become asteroids or planets. Gravity. This study suggests that planetesimals form almost immediately. If the asteroids were melted by something that only exists for a very brief time at the dawn of the planetary system, then the process of planet formation must kick off very quickly. Our study complements a growing consensus in the field that planet formation got going early, with the first bodies forming currently with the star. You know, they just talk. They have no idea. This is how it seems to me. Like they are like oxymoroning themselves time and time over again. And just to state an example, like the article we just read, which didn't really teach us anything, was made some 3 days ago. And this article is, what, 1.5 years old or something? Roughly. Maybe even more. Earth formed much faster than previously thought, new study shows. The precursor of our planet, the proto-Earth, formed within a time span of approximately 5 million years, shows a new study from the Center for Star and Planet Formation STAR Plan at the Globe Institute at the University of Copenhagen. On an astronomical scale, this is extremely fast, the researchers explain. If you compare the solar system's estimated 4.6 billion years of existence with a 24-hour period, the new results indicate that the proto-Earth formed in what corresponds to about a minute and a half. Thus, the results from Star Plan break with the traditional theory that the proto-Earth formed by random collisions between larger and larger planetary bodies throughout several tens of millions of years, equivalent to about 5 to 15 minutes out of the above-mentioned fictional 24 hours of formation. Instead, the new results support a more recent alternative theory about the formation of planets through the accretion of cosmic dust. The study's lead author, Associate Professor Martin Schiller, explains it as follows. The other idea is that we start from dust, essentially. Millimeter-sized object, all coming together, raining down on the growing body and making the planet in one go. Yeah, how should this start? How should it continue? You know, that's, again, gravity as the main force behind everything. Not only is this implication of the rapid formation of the Earth interesting for our solar system, it is also interesting to assess how likely it is for planets to form somewhere else in the galaxy. The bulk composition of the solar system. The key to the new finding came in the form of the most precise measurement of iron isotopes that have so far been published scientifically. By studying the isotopic mixture of the metallic element in different meteorites, the researchers found only one type of meteoritic material with a composition similar to Earth, the so-called Ci chondrites. The researchers behind the study described the dust in this fragile type of meteorite as our best equivalent to the bulk composition of the solar system itself. It was dust-like this combined with gas that was funneled via circumstellar accretion disk onto the growing sun. What? It was dust-like this combined with gas that was funneled via a circumstellar accretion disk onto the sun. I don't get that sense. If you get it, I'm happy for you. I can't. What? No, anyway, let's continue. Not too long anymore because This process lasted about 5 million years and our planets were made from material in this disk. Now researchers estimate that Proto-Earth's ferrous core also formed already during this period, removing early accreted iron from the mantle. Yeah, it just sank down. Probably this is what they mean. 2 different iron compositions. Other meteorites, for example from Mars, tell us that at the beginning, the iron isotopic composition of material contributing to the growing Earth was different. Probably it got electrically altered, Transmutation of the elements. SAM, the Structured Atom Model. Wal Thornhill, Anthony Peratt, Ralph Jurgens. You know the story. They don't. Well, anyway, most likely due to thermal processing of dust close to the young sun, the researchers from Starplane explain. After our solar system's first hundred thousands of years, it became cold enough for unprocessed CI dust from further out in the system to enter the accretion region of the proto-Earth. This added CI dust overprinted the iron composition in the Earth's mantle, which is only possible if most of the previous iron was already removed into the core. That's why the core formation must have happened earlier, Martin Schiller explains. If the Earth's formation was a random process where you just smashed bodies together, you would never be able to compare the iron composition of the Earth to only one type of meteorite. You would get a mixture of everything, he adds. I just have to question one thing. I would really, maybe I have to question this guy, Schildering. How many samples from Earth's core they have, which they can compare with this meteorite? I mean, really from the center of the Earth, a sample. They drilled whatever, a few thousand kilometers down there and took a sample from the Earth's core, and now that's the Earth's core sample and that's the meteorite, so let's compare it. I bet they have none. More planets, more water, perhaps more life. Based on the evidence for the theory that planets form through the accretion of cosmic dust, the researchers believe that the same process may occur elsewhere in the universe. This means that also other planets may likely form much faster than if they grow slowly from a random collision between objects in space. This assumption is corroborated by the thousands of exoplanets, planets in other solar systems that astronomers have discovered since the mid-90s. Explains center leader and the co-author of the study, Professor Martin Pizarro. Now, we know that planet formation happens everywhere. Really? Now that we have generic mechanisms that work and make planetary systems. When we understand these mechanisms in our solar system, we might make similar inferences about other planetary systems in the galaxy, including at which point and how often water is accreted, he says. Adding, if the theory of early planetary accretion really is correct, water is likely just a byproduct of the formation of a planet like the Earth, making the ingredients of life as we know it, more likely to be found elsewhere in the universe. Yes, hydrogen, oxygen. I have some pictures here. That's a screenshot from, see the pattern? I will put a link below to his channel. You can search for this. I don't remember which video it was. But he's talking about Birkeland currents. That's a Birkeland current. That's the Birkeland current simulator. In the electric universe model, galaxies, stars, and planets are connected together with vast electric currents. This explains why galaxies align like pearls on a string and give structure to the universe. Birkeland current. That's the Birkeland current simulator. And you can play around with that like this. You can do all kinds of things with this. You can zoom in or out and you can spin it around. And you can watch just straight into it. That's the Birkeland current. So that's some more things about the Birkeland current. And in the center of the Birkeland current, we have these iron, silicon, magnesium. A little bit farther out, carbon and sulfur, hydrogen, oxygen, nitrogen. And on the other side, helium. There is much more knowledge about this from example, Dr. Donald Scott. He can explain much more things about this. This is in a way how I think Earth might work. There might be a plasmoid kind of thing in the center of Earth. Here on the left, on the very left, we have a geoid, which is a dead stone. But it has similar features. If you look at the edge, where it's somehow making connections to the outer core, or to the mantle, crust, or however you want to call it. Thornhill's repellent core, things repel themselves. The electric force works attractive over long distances, but repellent in short distances. We have the magnetosphere layer, which is 16,000 kilometers away. The magnetosphere first layer, 3,000 up in the sky. The highest point of our atmosphere is the exosphere, somewhere 500 kilometers. These might be these kind of spots. Maybe I have to change the color. These kind of spots might be the hotspots where we have volcanoes. Where's the heat coming from? From below, molten material, which emerged from the plasmoid in the center. That's a part of a paper or article about global electric circuitry, an artist's rendering of the complexity of the global electric circuit. Colorado Boulder. There are many different kinds of circuits. Field-aligned currents, ionospheric potential, auroral currents, fair weather return currents, thunderclouds, and all kinds of things. And he's a professor at the atmospheric physics at the University of Reading in the United Kingdom. And that's made in Colorado. There are many interesting people living in Colorado. That is yet another example for Birkeland currents. Squatter man, like in Finnish mythology told, the heavenly pillar. And the ring, with those specific number of dots. And those people there, they are checking some dwarf planets, like really far away, in order to understand how Earth works. But you can stay on Earth. You can find very many interesting things on Earth too. That's from the plasma rock site here in eastern Finland. We have small craters. These are centimeters. So that's rather small. Here we have molten metal once again. And these parts here in between. If you look at them closely, they look like they are welded. We have tetrahedrons, many of them. I just marked a few. Tetrahedrons are those triangles, triangle-shaped features. And here's a little bigger picture of the welding part. I know the quality isn't that good, but I hope you can see that there is something different, because it's There's like, that's in a way the main seam, and they got splattered a little bit. And I think you can also see here like small tetrahedron shapes. No, we cannot zoom more in. And there is also quartz here, silica, which is rather red or orange. There might be iron or whatever else material mixed up in that. So the electrical force quite likely created also these rocks. So why it shouldn't work in another way somewhere else in the universe? We have proof on Earth about the importance and power of the electrical force. So be aware as we go into further into the changes what are going on, the intergalactic current sheet hitting our solar system and affecting all the planets and also Earth and the Sun. And if the jet stream patterns are changing as they are doing at the moment, this just means the cosmical Birkeland current and its diachotron instabilities, of which I have been talking, the same reason why. Is it Saturn, which has this hexagonal North Pole? Maybe it's Jupiter, or maybe it's another planet. I would have to look it up, but there is this one big planet which has a hexagonal North Pole cloud pattern. It's basically the same on Earth. If the input is fluctuating, the shape will fluctuate. If the shape is fluctuating, we are getting different kinds of patterns in the wind. So now let's go quickly over to Null School and check it out if there's anything visible of what I have been talking about. Here it's not that well visible. Also not here. Let's check out the southern side. No, it's not also. We have to maybe go down a little bit. But I would say that's rather elongated. You know, it should be more round. But that's natural fluctuation. Here we can probably see some of those diachotron. Here is one. Here is one. Here is one. Here is one. Yeah, it's a little bit distracted. These might be the Himalayas, so we cannot count them. So there is now at the moment maybe four of these structures visible. And these are just the instabilities from the Birkeland current. And they are different in different heights. And if you imagine, can we zoom still out? If you would imagine this would be the Birkeland current connecting us, which goes through Earth. And if it's changing in position or in fluctuation, of course the wind pattern will be different as well. That's why the wind patterns are changing. From above seen it would be like this. And there are the diachotron instabilities, which I have found once in a mosaic. On Google Earth somewhere in the Balkan region. Diachotron instabilities. And Birkeland currents. And all these other instabilities which are going on. And we have a double helix also on the outer side. And maybe something like the heavenly pillar drawn here in the back of this whatever animal that is. Horse, cow, donkey. I don't know. But there are many interesting things in this picture. But I leave it here. That was a very long video. I didn't get anywhere, but thanks. Bye.